Hello everyone and welcome back to the Python 2 Memorial Concert Hall. Next up we have Katie Bell with text fast full punctuation. There must be a better way to code. Katie has been a professional developer for more than 10 years and has been a friendly face in Python communities for a lot of that time. Please feel free to share your experiences, comments, and questions in chat and Venulus throughout to join the conversation. Thank you.
All right, let's get into it. My talk is there must be a better way to code. And what I mean by this, when I talk about the way that it is now, is this process where we write code by typing characters into a text file, right? You might use an IDE, you might have the most complicated Vim macros ready, available to you. But ultimately, most of what we do with code is writing characters into a text file. And this is a pretty good way to write code. A keyboard is a really fast way to enter code into the system. And we have this idea in our heads that when we write code, if we're a really great programmer, we'll look like this. And we're typing line after line really fast, and the computer's doing exactly what we want. But I have spent a lot of time watching people write code. I've done a bunch of teaching, I have done pair programming, I've done live coding interviews, and I've even watched people live stream their coding process online. And when people write code, it doesn't look like they're typing super fast. What it looks like is something like this. It's actually quite awkward to watch. So I'm going to put you through a little bit of that pain, and we're going to watch someone write code. And this is in VS Code. Just ignore the things that pop up. VS Code is doing its thing. And so we write code. Okay, we haven't made any mistakes yet. It seems pretty fluent. Write another line of code. All right, we're taking that people variable, we're dividing it. Okay, but there's a problem here. That people variable is coming out as a string from the input function, and now we're trying to divide it. So we need to fix that. So we go back, go back to the beginning, we wrap it in an int function. We then have to go to the end and add the close bracket. And we want to change this print function a little bit. Oops, there was a typo there, we fix that. We add another string to this, and then we go back. Well, we need to make that into a string so we can add it to the other string. So we go back, we move the cursor over, and then we put the close bracket in. We put the close bracket in the wrong place, and it's still syntactically valid, but we then need to fix up the white space. So we've done a little bit of extra work there just to sort of tidy up the code. And this is not a terrible way to write code, but I want to look in a little bit closer at what's actually going on as we're writing those edits, because we're not just writing lines of code left to right, top to bottom. We go back, we edit the code, we fix things, we change it. So looking at this program, in case you hadn't already figured it out, this program is a thing to help us divide up the Tim Tams in a packet. So Tim Tams come with 11 biscuits in a packet. That is difficult to divide up because it's a prime number. So we have a little program to help us. And this program asks, how many people want Tim Tams? Maybe there are 4 people. That means everyone can get 2 Tim Tams each, but then there are 3 left over that we'll have to fight over. So fairly simple little program. And we're going to dive into what is actually going on as we're writing this program. And when you run a Python program, this is the process that it goes through. You start off with a text file. And when you give it to the Python interpreter, the first thing it does is parse that file into the AST, the abstract syntax tree. And that AST is the structure of the code that is then used to generate the bytecode that then is run in the Python virtual machine as you're executing your Python code. And we're going to zoom in on this AST part and have a look at what is the AST for that code that we just wrote. And conveniently, Python has a module called AST, which lets us inspect and manipulate and edit the AST for a piece of code. So it's very simple to use. I absolutely recommend trying this at home. You can use ast.parse and you give it the code, and it gives you back a tree. And that tree is the tree structure representation of the code. And there's a convenient ast.dump function, which lets you dump out the tree so you can have a look at it. And it looks something like this. Don't bother reading this. We're going to break it down. So at the top level, this tree structure starts with a module, and that module has a body in it. And in that body, we have a list of statements that make up our program. And this program has 3 statements. The first one is an assignment statement. And then there are 2 expressions where we're calling a function, so a function call expression. And so the top level of our structure looks a little bit like this. But as we were writing the code, we started off with the first line of valid code that we wrote looked like this, right? We had our assignment statement, and we're assigning to the people variable. And the value that we're giving to that people variable, we get from another function call expression. And the arguments to that function call expression are a string. And that string is the how many people want Tim Tams string. So we have our little tree structure. It's a fairly simple structure. I have simplified it a little bit from what it does look like in the AST. But when we add that int, so that we're converting this to an integer before we store it in the people variable, we got another node in our abstract syntax tree now. And that is another call to the int function. And we haven't changed any of the other nodes in our tree. We've just added one in. And even though we did 2 edits to our line of code, one at the beginning and one at the end, we have done 1 operation to our tree. Looking at the next line, we started out with a fairly simple, okay, we're printing the people variable divided by 11. And here we have that division sign, the integer division, is the binary operator called floor div in the AST. Now, floor div has a left side and a right side where it divides the left side by the right side. And the result of that binary operation is then given to the print function, which then prints it. And when we added to this, we added another string. So we have another operation, a binary add operation. So these operators aren't just kind of going left to right. They are structured in this tree. So our add operation takes the result of the division operation and then adds it to a string. Now this is going to cause an error. So we need to do one more edit. We need to add a string function, add a call to the stir to convert that integer into a string before we do the addition. So that is adding another node into the tree. And the take home I want you to get from this is that when we are editing the code, we're not just editing characters in a text file. We are doing tree operations on our code tree. The fundamental structure of code is a tree. And when we edit that code, we're doing operations on that tree. We are adding nodes. We are removing nodes to that tree. And we are taking some nodes and moving them to reattach them somewhere else. And you can express all of the operations that you do on code in this kind of form. And when you're writing code, even though you're writing code in a text file, what you're doing in your head is manipulating this tree and then translating the change that you want in the tree back into the code. And you do this mostly without realizing that you're operating on a tree in your head. And the question I want you to be asking is, why do we do it this way, right? We have a text file, we convert it into a tree, but it was already in my head as a tree. Then that tree is converted into bytecode, and that bytecode is run on the Python virtual machine. And we could have it work in a different way. We could have something else that will construct this abstract syntax tree, some other interface where we could manipulate our abstract syntax tree and write our code without it having to use that text form. If the AST for Python isn't exactly what we want, maybe we have a different tree structure, and that different tree structure could generate bytecode. There's no reason we can't do these things. And in fact, people have, not necessarily with Python, although I have seen it done with Python, but there are coding interfaces that are out there that are not text-based files where the code is a bunch of characters sitting in a text file. And generally, we would call these visual coding or visual coding interfaces. And we're going to go through a couple of example visual coding interfaces to see how they work and see how their tree structure works and what the pros and cons are for these visual interfaces. And when I talk to people about visual coding and interfaces other than text, one of the ones that comes up the most is Scratch, because it is really popular. And a lot of people have maybe not always used it, but at least seen it or heard of it. And it is a very popular interface that helps beginner programmers and students and kids learn to code for the first time in a way that's easier than writing a text file. And it looks like this. once it loads. So we have a series of blocks, and those blocks make up our program. And when we want to add a new block, we don't need to magically know what it is that we want to type. We can search through the list of blocks to find something that we want to add, and we can insert it into the program. And you'll notice that we have binary operators like we saw in our AST, and those binary operators we can then kind of put into the code. So when we're writing the code, we're generally doing, again, more tree operations by manipulating the structure of the code in a visual way. And Scratch is a really great language. There's a reason that it is so popular for teachers and for kids, because it is really easy to get started with, and it's very easy to understand and manipulate the code, even if you've never seen code or understood code before. But it is not something that you would see people using in the real world as like a paid professional programmer. And there are a number of reasons for this. This is absolutely not what Scratch was intended to do. It has a fairly slow runtime. People have made amazing programs in Scratch, little platformer games and quite complicated things, but it still isn't at the level of performance that you would get from professional tools. It is not something that people would use in the real world for some kind of product that they wanted to sell. And it has a fairly limited set of functionality that is not the level of range and freedom and low-level functions that are available to you in a more mainstream programming language or a text-based programming language. But the biggest criticism, and this is the one that kids butt up against once they have been doing Scratch for a while, is even though you know exactly what block you want to put into your program next, you have to go and find it and drag it over. And that process is slow. It's great for when you're beginning and you don't know what block it is that you want to use next. But when you have been doing Scratch for a while, it becomes very tedious to have to go and search for the block that you want. So we're going to go through these one at a time, because these are often things that are cited as to reasons why visual coding doesn't work or can't work. And I want to debunk those. The first one is a slow runtime. We've already kind of seen that we could create an AST or some kind of tree structure and then use one of our existing runtimes, like the Python runtime, or we could compile it. There's no reason why a visual coding language has to have a slow runtime, so we're just going to move past that one. But the no real world use one is interesting, because there are visual coding languages out there that you might not have seen or heard of that do have real world use. And the first one I want to focus on is from Unreal Engine. And you might have heard of Unreal Engine. If not, you might have heard of some of the games that have been written with Unreal Engine, like BioShock or Fortnite. And Unreal Engine has a visual coding system in it built into the tooling. So as an example, we're going to look at this little game where there is a player, and on the ground, there's a kind of white panel. This is our box. And we're going to look at the code for what happens when that box is interacting with something. So this is blueprints, and I have taken this directly out of the blueprints tutorial. So nothing particularly fancy going on here. We have, I'm gonna grab my pointer. We have this red box here at the start. This is the on component begin overlap. So this is an event handler for the event that happens when something overlaps with this box. And we can follow this white line to see what the execution flow of the program is. The first thing that it hits is a branch, which is an if statement. And that branch has a condition, which is an equality operator. So look very familiar. And it's checking if this actor that has interacted with the box, that has collided with the box, is equal to the player. So we're just making sure that the thing that touched the box is the player. And this is a binary operator, just like the one that we've seen in our AST in Python. And if that binary operator returns true, it will then cast the object to a character object. And this is not a beginner programming concept, casting, right? This is a fairly featured programming language. And that character object, we can then call a function on that character, which is the launch character function, and we give it a launch velocity in 3 dimensions. And what does this do? Well, when we run this blueprint, the player can interact with the box and be launched into the air, right? And this blueprints tool isn't something that is specifically targeted at beginners, right? This is something that is used in the professional games industry on professional games. It is, to a certain extent, targeted at people who would be otherwise very uncomfortable with C++ code, like designers, artists, but it is also used by professional developers because sometimes it is nicer to use when they're working on the interactions for particular objects in the game. So it is something that is used by professional C++ developers as well, because sometimes it's nicer. So I'm going to cross out no real world use because we do have examples of visual coding languages that are building our code trees in the real world for professional developers. The next one I want to look at is whether or not visual coding languages have to be slower to edit than text programming languages. And one of the things that's interesting when you ask people about blueprints is that sometimes writing the logic in blueprints is faster than writing the equivalent C++ code. And game developers, depending on what it is that they're writing, would sometimes use blueprints because that process of iterating on it and editing it and experimenting with it is faster than writing the code and then compiling it. The cycle is shorter. But you've probably already used a visual coding interface for editing code because it's faster, and you wouldn't necessarily have realized it. So if you've done any web development, you've probably used this. And this is, of course, the Chrome inspector. So here I am. This is the 2020 PyCon site. And I've opened the Chrome inspector, and I can navigate through the tree structure of the DOM in this page. And I've got the CSS here as well. And so I can, going to go back, try that again. In the CSS, I can check and uncheck these little checkboxes to edit the code. These like curly braces that you see here in the CSS, they don't have to be there. We're not actually editing a text file. We are manipulating the structure of the CSS and styles on the page. It just happens to be in a way that looks a lot like the code, but we're not. This isn't saved to a text file. This isn't a text file edit that I am doing as I'm manipulating these numbers up and down. And it lets us do nice little things like you have a color picker when you're choosing the color and you don't have to type out an RGB value. So we use the Chrome inspector to edit CSS when we want to iterate and develop because it is faster than writing the equivalent CSS and then reloading it into the page. And it doesn't do exactly all of the things that you can do with CSS. You still have to, at some point, have a stored file, which is your CSS. But all of the examples we've looked at have in some way a limitation that doesn't let you do every single thing that you could do with an equivalent text-based language. And so as a last example, I want to look at this one, which is Bolt, which is also from a game engine. This is from Unity. And Bolt is an interesting language because it was specifically designed to be a one-to-one translation of C#, the scripting language in Unity. And Laszlo Bonin, the creator of Bolt, said, if you're a coder, you probably won't need the flow graphs in the Bolt interface because Bolt gives you pretty much a one-to-one translation of the code. Anything you can do in Bolt, you can do in code. And he kind of expects that coders will want to code in C# instead of in Bolt. But the point here is you don't have to choose one or the other. They are functionally equivalent. And this is making some assumptions because Bolt version 1 does have some limitations, but there is a Bolt version 2 coming out, which I believe is meant to not have such limitations. But if we have a closer look at Bolt, this is also an event handler for a collision event. And we've got here a collision that happens between another branch with an if statement where we check if the thing that we collided with is an enemy. If it is an enemy, we create an explosion and we use a minus operator here, subtraction operator, to reduce the health of the player by the amount of by the magnitude of the force with which the collision happened. And as you're editing this Bolt code, it is also generating the C# code, right? These are functionally equivalent. There are other issues that do come up with visual coding editors that I don't have examples to debug. And these are things like when you have these graph layouts with lots of lines, when you get complex code, it starts to look like spaghetti. And it's very difficult to kind of keep it laid out in a logical way. And the other thing you'll notice is, especially with Bolt, is this code takes up a really large amount of space on the screen. You can't fit a lot of code into your screen. And down here we have the equivalent C# code, which is in a much smaller space. So that information density is a factor for a lot of visual coding languages as well. But I want you to imagine that we live in this idealistic future world where we have solved these problems. And imagine that our code is stored as a tree, and that tree is just a pure tree. It doesn't have any of the information about how it should be laid out or displayed to the user. It doesn't have white space and wrapping and all that kind of stuff built into it. It is just the logical code tree. And the way that it is displayed and edited is up to the editor itself. So just imagine this world, because it's a nice world, right? We don't have to deal with style guides. Maybe we still have style guides for naming conventions, but otherwise we wouldn't have to have Guido wasting his time doing a change that is purely style edits. And none of us would have to fix up the styling as we go, because it's something to do with the editor and the way the editor is displaying it. If you wanted to have very large indentation in your code, you could. That is an editor setting. It doesn't affect anyone else who is editing the same code. And we wouldn't have to spend our time arguing over tabs versus spaces or how many spaces, because that is up to you. It's your choice what your editor settings are. On that note, we also would have fewer merge conflicts, right? In this example, I have taken our TimTam code and I have wrapped it in a function, and I haven't changed any of that code. This is actually a non-functional change, but Git will tell me that I have changed every single line of this code. And if we were expressing our edits to the code in a tree form, we would be able to merge a lot more of these edits in a sensible way where we know it's safe. Because even though they're affecting the way that the code is represented, those lines of code themselves haven't changed. This would also mean that if you have a patch on something upstream, it would be easier to maintain that patch because it would conflict less with the other edits that are happening upstream. We might also end up with different editors that suit the different kinds of devices that we have, right? Editing code while typing punctuation with wide lines and bad wrapping is going to be painful on a small screen or a touch device, but we might be able to have different editors that are better suited to these different devices if we weren't including the way the code is laid out as a part of the code as it's stored. We might even have support from multiple languages, because the way the code is displayed is separate from the underlying structure of the code. We would have to translate things like function names and variable names, but popular libraries could have translation packs and it would be workable, right? If we have the way the code is displayed and stored separated from the structure in which it's stored. To do all of these things though, we would be breaking free of everything that we have already. All of our tooling, all of our IDEs and our version control systems, all of these things are built around the world of text. And I think we will break free of this world, but it is going to be quite a long transition, and it means relearning and rethinking almost everything about how we write code. But I think that world will be a better place, and it will unlock a bunch of cool things that will make our lives easier as developers if we can get there. So thank you. I would appreciate questions, discussions, comments, anything. I want to have, this is the sort of thing where people have a lot of different ideas that are all really great. You might also notice that later on today, Nick is giving a talk, which is on a very similar topic, but he's going to have a very different take on it and a different perspective. And I'm really looking forward to that talk. So if you want to think more about this, absolutely go see that talk. But otherwise, I think we are out of time for questions.
Great. Thank you very much for your presentation, Katie. There's been some great chat in the Venulus platform about it during the talk, which would be great to read through later. I reckon this definitely gives us all a lot to think about, and I appreciate the breaking down of barriers to visual coding in a really visual way as well. Next up, we have a long break for Australian lunchtimes. I hope folks get up, rest your eyes, maybe eat some food, or maybe rapidly write your lightning talk submissions because they close in 30 minutes at 12:30 ACST. I'll be dropping the link in chat, but if you have anything you want to talk about, it doesn't have to be Python related. Drop a submission in the link that I'll drop in chat. Thank you so much, Katie.
Thank you.